Hi everyone, welcome to our continuation of our lesson 1.3 on evaluating limits analytically. Just to recap what we've discussed in class so far on evaluating limits analytically, we've talked about using direct substitution, some basic limits, some properties of limits. We've looked at limits of polynomial and rational functions. We've looked at limits involving radicals, limits of composite functions, trig functions, and functions that happen to agree at all except one point. We've gone through 6 different examples that you should have in your notebook, and right now we're going to look at a strategy for finding limits. So with this strategy, the first thing you're going to keep in mind is you are going to try to recognize which limits can be evaluated with direct substitution. If you can use direct substitution, that is going to be the best method you can do right away. If, however, you cannot do direct substitution, we'll move on to a different step. So if direct substitution can't work, what you're going to do is try finding another function that agrees with the original at all points except for c. So except for whatever value x is approaching. And then if that doesn't work, we can go back to what we did in lesson 1.2. We can use a graph or a table to solve the limit. So let's look at our next example, example 7, which is the dividing out technique. So we are going to try to find the limit of x squared plus x minus 6 over x plus 3 as x approaches negative 3. So first, let's try using direct substitution. Let's put negative 3 into the numerator and then into the denominator, and we'll see if we can actually use it. So we're going to do negative 3 squared plus negative 3 minus 6 all over negative 3 plus 3. In our numerator, negative 3 squared is just 9. When we add a negative 3, we can just make it minus 3. Minus 6 all over negative 3 plus 3. In our numerator, 9 minus 3 minus 6, that simplifies to 0. And in our denominator, we get negative 3 plus 3, which is also 0. And we know that through division, we can't divide by 0. So our limit's not going to actually work by using direct substitution. So we need to try a different method. So since direct substitution didn't work, let's see if we can factor x squared plus x minus 6 and see if we're able to find a common factor between the numerator and the denominator. An x squared plus x minus 6 is factorable. It's going to factor into an x plus 3 and an x minus 2. And we can put that over our x plus 3. This is just a technique where we are finding another function that will agree with x squared plus x minus 6 over x plus 3 at all but the 1 point. Because here, what we can now do is we can cancel out our x plus 3. So all we'll be left with is an x minus 2. And in this case, we can now use direct substitution to calculate our limit. We can take our c value and put it in for x, have negative 3 minus 2, and we'll find that our limit is negative 5. We can confirm this if we create a table or look at a graph of this. We'll notice that as our x approaches negative 3, our y value is going to come to, never actually equal, but get close to negative 5. So the limit of this function as x approaches negative 3 is negative 5. So now let's look at our next example, example 8, which is a rationalizing technique. And we'll use this technique when we notice there's a square root or any kind of root radical in our limit. So let's look at this when we have the limit of the square root of the quantity x plus 1, and we subtract 1 from that, all over the value x, as x approaches 0. So if we do this by direct substitution, we're going to get the square root of 0 plus 1 minus 1 over 0. And it doesn't really matter what we're going to get in our numerator because our denominator is going to be 0. We can't divide by 0. So direct substitution is not going to work in this particular problem. So with the rationalizing technique, what we're going to do is we're going to take our function, the square root of x plus 1 minus 1 all over x, and we're going to multiply it by a factor of 1, but that factor of 1 we're going to use is going to be, so to do the rationalizing technique, we're going to multiply the numerator and the denominator by the conjugate. And as a review, conjugate just means we're taking a rational expression or a radical expression and we're changing it essentially. We're going to change the square root of x plus 1 minus 1, and we're going to multiply that whole expression by the square root of x plus 1, and this time instead of minus 1, we're going to change the minus to a plus. We're going to do that in both the numerator and the denominator. Essentially, it's very similar to going x plus 1 times x minus 1. We're essentially going to square the first term, and in this case the first term is the square root of x plus 1, square root of x plus 1 squared minus the second term, squared, 1 squared. And then in our denominator, let's leave it as x times the square root of x plus 1 plus 1 for now. We might have something fancy that happens shortly. When we square a square root, they undo each other. So in our numerator, we're going to be left with x plus 1, and then 1 squared is 1, minus 1 over x times the square root of x plus 1 plus 1. And in our numerator, x plus 1 minus 1, that's just actually going to simplify to x, because the plus 1 and the minus 1 are going to cancel each other out. So we can just get rid of that. And now both our numerator and denominator have a factor in common. So it was pretty convenient we didn't distribute that x to the square root of x plus 1 yet, because we can cancel it out. And now in our numerator, we'll just have a 1 over, in fact, our new expression, not just in our numerator. Our new expression will be 1 over the square root of x plus 1 plus 1. And now we can find the limit with our direct substitution. We'll put 0 in for x. I am going to erase what's here on the screen just so I have enough space to continue my work. So just going off of what we just did, we're going to have the limit of 1 over the square root of x plus 1 as x approaches 0. So now let's just put 0 in for x and figure out what we get. We're going to have 1 over the square root of 0 plus 1 plus 1. 0 plus 1 is just 1. So we've got 1 over the square root of 1 plus 1, and the square root of 1 is 1. So we've got 1 over 1 plus 1, and 1 plus 1 is 2. So we get 1 half. So the limit of the square root of x plus 1 minus 1 all over x as x goes to 0, the function will never give us a y value of 1 half when x is 0. We can't find that. But if we were to graph it or look at it in a table, we would notice that it will get closer and closer to y being 1 half as x gets closer and closer to 0. So this leads us into our next theorem, theorem 1.8. We're going to call it the squeeze theorem. All this theorem says is if we have some functions, we'll call them h of x. If it is less than or equal to, I can't make the less than or equal to sign, so I'm doing a less than and an equal to symbol. If that's less than or equal to another function, we'll call f of x, and that is less than or equal to a third function we'll call g of x. For all x's in an open interval containing a value c, except possibly at c itself. And if the following is true, both the limit of h of x as x approaches c, if that equals L, and then L also equals the limit of g of x as x approaches c, then we say that the limit of f of x as x approaches c, it does exist, and it's equal to L. Because if the two functions it happens to be between have a limit, and that limit's the same, then f of x has to have a limit, and it's going to be the same. And before we look at an example, we're going to look at one more theorem. This theorem is theorem 1.9, and it's two special trig limits. Our first special trig limit is going to be the limit of sine of x over x as x approaches 0. If you ever see this, the limit is going to always be 1. Our second special limit, if we ever see that we have the limit of 1 minus cosine of x over x as x goes to 0, this will always equal 0. So let's look at another example. example 9. And this example is going to be finding the limit of tangent of x over x as x goes to 0. So a little side note, we should recall that tangent of x is equal to sine of x over cosine of x. We're going to use this to solve the limit. So we're going to actually replace tangent of x with sine of x over cosine of x. So let's do that. Let's rewrite this limit with that. We're going to have the limit of the sine of x over x times the cosine of x as x goes to 0, where this sine part right here and this cosine part are from replacing tangent of x with sine x over cosine x. This x in our denominator is still the original x that was in our denominator. So now let's use some of the properties we've learned so far. And one of the things we've learned so far is we can break this limit up. We can break this into the limit of two separate functions. This is kind of a composite function. We can have the sine of x over x, and then we can also have 1 over the cosine of x as x goes to 0. I know that's like magic, but if we actually multiplied sine x over x by 1 over cosine x, we get our sine x over x cosine x back. Now we can break this up and do two separate limits. So let's try that. Let's first just find the limit of the sine of x over x as x goes to 0. And in fact, this comes from our last theorem, Theorem 1.9. This is one of those special trig identities, or trig limits. This will always equal 1. So we're done finding that part. Let's now find the limit of 1 over cosine of x as x goes to 0. And if we use direct substitution for this, we'll have 1 over cosine of 0. And the value of cosine, when our measure is 0, is 1. So this is going to be 1 over 1. You can confirm that using your unit circle. And that's just going to be 1. So now to finish this limit, this is a product of two limits. We can just take our 1 from our first limit, and we can multiply that by our 1 from our second limit, and 1 times 1 is just 1. So the limit of tangent of x over x is going to just give us 1 as x approaches 0.